Public clients like mobile applications cannot securely store a static client secret. The standard authorization code flow is fundamentally vulnerable to interception attacks because an attacker can capture the redirect and exchange the code for tokens. Proof Key for Code Exchange, or PKCE, mitigates this by requiring a dynamically generated secret for every single transaction. This secret is never transmitted directly over the insecure front channel. PKCE is mandatory for native applications and single-page applications because they operate without client authentication. We use a cryptographic hash function, specifically SHA-256, to create a challenge that only the original client can solve during the token exchange, binding the authorization code to the initiating device instance. The PKCE flow begins with the client generating a high-entropy, cryptographically random string called the Code Verifier. This verifier must be between 43 and 128 characters long, using the unreserved characters defined in RFC 7636. The verifier must be generated using a secure random number generator, not a simple pseudo-random function. In iOS, use seq_random_copy_bytes. On Android, use secure random. The client must store this original code verifier securely in temporary storage, typically the application's secure key-value store, until the token exchange is successfully completed. This verifier is the secret key for the entire transaction. The next step is computing the code challenge from the verifier. The standard and required method is S256. This involves taking the SHA-256 hash of the raw code verifier string. The resulting 32-byte digest is then base64 URL encoded without padding characters. This base64 URL encoded string is the code challenge. For example, if the verifier is 64 bytes, the SHA-256 hash yields 32 bytes, which is then encoded. The client sends this challenge to the authorization server, proving it possesses the verifier without revealing the verifier itself. The authorization server stores this challenge associated with the session. The client initiates the flow by opening the system browser or a custom tab, directing the user to the authorization server's authorize endpoint. The request must include 5 specific parameters. First, client_ID, identifying the application. Second, redirect_URI, which must be a custom scheme or universal link registered by the mobile application. Third, response type set strictly to code. Fourth, the code challenge, which is the S256 hash we just computed. Finally, the code challenge_method, which must be set to S256. The redirect_URI ensures the authorization server redirects back to the application, not a generic web view. After user authentication and consent, the authorization server redirects back to the mobile application using the registered custom URI scheme, such as myapp://auth. The application must parse the incoming URI query parameters to extract the authorization code and the state parameter. The state parameter must be immediately validated against the values stored locally before the initial request. If the state values do not match, the request is a cross-site request forgery attempt, and the application must abort the flow immediately. The authorization code is short-lived and can only be used once, making the subsequent token exchange time-critical. The mobile application sends a post request directly to the authorization server's token endpoint. This request is the critical step where the proof key is utilized. The request body must include the authorization code received in the previous step, the client ID, the grant type set to authorization code, and the redirect_URI. The unique PKCE requirement is the inclusion of the original unhashed code verifier. This verifier is sent in the request body, not the URL, ensuring it is protected by transport layer security. Upon receiving the token exchange request, the authorization server performs 2 key validations. First, it verifies the authorization code is valid, unexpired, and matches the client ID and redirect_URI. Second, the server takes the received code verifier, hashes it using SHA-256, and then base64 URL encodes the result. This newly computed challenge must exactly match the code challenge value stored in the server session associated with the initial authorization request. If the hashes match, the server confirms the client is the legitimate initiator and issues the access token and optionally the refresh token. PKCE effectively prevents the authorization code interception attack. If an attacker intercepts the authorization code during the redirect, they cannot exchange it for tokens because they lack the code verifier. Since the verifier is never transmitted in the front channel, it remains secure within the client application. This mechanism ensures that even if a malicious application registers the same custom URI scheme, it cannot complete the token exchange without the corresponding verifier.
This binding of the authorization code to the specific client instance is the core security benefit of PKCE for public clients. Implement token storage using platform-specific secure mechanisms, Keychain on iOS and Keystore on Android. Never store the code verifier in standard preferences or local storage, as this exposes it to potential compromise. Ensure the code verifier is deleted immediately after a successful token exchange, or if the flow fails due to an error response. For production readiness, enforce transport layer security for all token endpoint communication. Regularly audit the entropy source used for verifier generation to ensure true randomness, preventing predictable challenges and maintaining cryptographic integrity.